Good morning, everybody. Again, good to see that you came back. No? So this morning we have the first radio astronomy class. So today will be like radio astronomy 101. The basics. Why radio is important? What can we do with that? And in the afternoon at 2 o'clock we have the hands-on. So the tutorials. I send a link with the data to download that we are going to use in the tutorial, and also the software part to install. Apparently, everyone said it's easy enough to install for me. Good. And after this class, we have a coffee break in the cafeteria, so you are all welcome to join and we can discuss more. So Rafael and Tom will be sharing this first class, so the floor is yours, and thanks for being here.
Thank you. So for the tutorial this afternoon, we're not really sure how to organize, in the sense that I can do something on the screen, you can do something yourself. We will be very flexible, open for suggestion and wishes. Also, if you want to have your own data set to display.
Someone's echo has the sound on. Okay, go here.
Oh, sorry. Is that what?
Yeah, you can share microphone.
It does. It should be.
No, I think it's good. I silence all the participants.
Okay. Okay, so so yesterday you have been thrown into the data cube and the visualization and the position velocity, wonderful, needed, of course, for the visualization. So what we would like to do today and Thursday is a step back and see more about the radio, what can do for you, how complicated it can be, and what to watch out for. So if you are interested in using radio data, I mean UV visibility that you will hear about later, that's not what we are going to do because that's too much, too complicated to do the full process. So in a way, so then you should come to Groningen in April. We will have a mini radio school with also data reduction and all this. So the idea here is that essentially you take an image or cube from a public survey or from data available to you, whatever, and you want to do some analysis with them. But even those data can have a problem, so we will look into that, but not the full calibration of the visibility flagging and all this. There's no time for, essentially. It was supposed to be a fun masterclass, so that part is the boring one, so we skip. Okay, so that's the first warning. And so today I'm going to cover the part on the radio continuum. So you will see what it means with that. And so the first part is why even bother about thinking about using some radio continuum, what can do for you. And then the second part is that Tom will do is now interesting, but how does it work and what are also the problems that you can encounter. And then the afternoon, of course, practical. So the radio, in the radio regime, let's say we go from meters to millimeters wavelength. These are what I would call radio. And the emission that you will see is mostly due to synchrotron, so non-thermal, but we will get to that in a moment, is made of continuum emission. So the emission that you see at all the wavelength or frequency that you observe, these are the typical frequency. 1.4 is in a way the central frequency we like. This is the low frequency that low far does, and all the high frequencies, so alpha will be up here. And so the continuum part that is mostly a power law, but we will see more about that, and then the line that makes your nice data cube. So this continuum can come from emission from many objects, so different type, and is polarized very often. So it has a number of interesting properties that could be not only for AGN people like me, but normal galaxy can be relevant. And on Thursday, we go to the line part. So, so one thing that I wanted to mention is that the continuum emission that you can see in a radio image is usually one image. So yesterday, Thijs gave a lot of space, of course, to the cube, because that is where the visualization is more interesting, of course. While the continuum, usually you take whatever you observe, you squash all the channel, and you get the continuum part. So it's different, also in the way it's easier, at least to look at. So it's not a cube. So I will be talking about image also this afternoon. And the first step will be just to look at single image. That's not always completely true. With the new radio telescope, the band can be so large that you can split in multiple, and you can make a multiple image, a slightly different frequency because the band is so large. That's the second level fanciness. For the moment, let's assume you take whatever you observe, you squash, you get one image. Okay, so I've displayed here some of the radio telescope that we have available. Note that the radio telescope, almost all are at open sky facility, so you can apply for time. I think on all of them, all of this one, you can just apply for time. You may not want to apply for time. That's different. Like the LOFAR, you definitely don't want to apply for time. So you just want to take the data that somebody else has used for you. But that's a different story. In principle, you can apply for time. So what I wanted to show here is how different the radio telescope, the hardware can be. So you see here ALMA, nice, beautiful dishes, very well a surface, very highly precise surface. And here you see LOFAR that are just dipole, because the wavelength here is so large that you actually so long, a couple of meters for the high band, 30 meters for the lower, that you don't even need a dish. A dipole is enough. So you have a variety of instruments, like the GMRT is just a net of, because also there you work at a low frequency. So the lower frequency you get, the more primitive your instrument is, at least to see. Then what happens behind the scene, that's the complicated part. But okay, we skip that. But anyway, you have a variety, and so you can choose which telescope you use depending on your science, of course. And I'm going to focus on interferometer, and so I'm going to skip the single dish because the resolution is too low, and you will see from the part of Tom what this means. Of course, the single dish are interesting for some science. No blame on that, but there is a limitation in the resolution, so it depends what you want to do. The comparison with the optical, for example, may not be the idea. Okay, so I wanted to start with some examples. So you have a variety of radio telescopes, you have a variety of frequency. Let's give you a kind of parameter space. So if you look for data on public survey, like the one that I gave you, and a list in the document. No, there was no list. Okay. This afternoon there will be a list of public survey. You can see how different is the radio emission that you get from the same object. And so, depending on your science, what you want, what you need. So let me start from our galaxy. This is the old but still super important survey at 400 megahertz, so a low frequency is 70 centimeter wavelength, done with single dish. So you cover the entire sky, north and south, and the dust lane, of course, the dust and galaxy disk, everything. That's good for some science. Of course, for other science, the major improvement came with Meerkat. These are the observations done with the telescope in South Africa, the new one, at 1.3 gigahertz, so 20 centimeters, more or less. And you see, this is arc-minute resolution. This is 10 a second, 15 a second, thereabout, yeah. And so here you see all the details, all the supernova that are there, the galactic center, all this, the filament, the funny filament that they found here. But this, although it's a mosaic, covers only this part. And it took forever to do. You really need to be a very good radio astronomer to do this. So it depends what your goal is. So I have a few more examples. I thought to put the ExGal favorite galaxy in it, M11. So this is the H1 that you have seen in all the posters everywhere, superposed to the optical, okay? And these are continuum image. So not the line part, but the continuum, the synchrotron, most of it, that you detect. So this is, if you take the public survey called NPSS, the now VLA Sky Survey, 1.4 gigahertz, 45 arc second resolution, shallow survey. So this is what you see. This is what you see if you take the first, that is also a VLA survey done with a different configuration of the array at the same frequency, 1.5 gigahertz, but at 5 arc second resolution. So more similar maybe to your optical image. And this is what you see. Almost nothing, but you see the center of your object. So if you are interested in what is happening there, or in some object close, that's your survey. This is the plus, a very large array sky survey, also with the VLA, but at 3 gigahertz and 2.5 arc second resolution. So this is what you see. So this is the same field, the same object, with 3 different surveys.
When you say a frequency, you're collapsing within some range, or
These are plus or minus depends. These are all the data. So it was only 50 megahertz at the time of the band of the VLA. So it was very narrow, but it collapsed. And also this is a certain. This has a broader band, but everything is collapsed. So one image, one frequency. That's it. But if you look deeper, you actually see more of this galaxy in continuum still. So this is the Abberthief image, and this is still continuum emission, synchrotron emission from whatever is in your galaxy. This is 1.4, so it's the same frequency as these two, but it's a deeper observation at 10 a second. So you go deep, and then you pick up all the structure. So you should be aware, if you take this image, you see something, but you miss other factors because it's just too shallow. And this is a low, 150 megahertz, so low frequency, 6 arc second resolution. And also here, you see the structure. You see also how the continuum match the structure of your optical galaxy. So this is just a warning. It's not good or bad. It's just something to keep in mind if you use this that are really useful survey, but some limitation.
Sorry, but what's the difference in exposure time? That's the last
Sorry?
The difference in exposure time. Maybe we can say.
Certainly. So this is a survey of the entire northern sky. So in order to do this, they had shorter observing time on each pointing. But you get the entire northern sky. So any object that you want, you can go to the MBSS and check. First, it's not the entire sky, but it's a big chunk of the northern sky. So, yeah, they could not do better than this. This is even shorter, because as you have higher frequency, you have a smaller field of view, so it takes even longer to do the entire area. So they did snapshot. Terrible. But you get a lot of sky, so depends. While these are longer observation.
But longer is
So this
1 hour, 3 hours.
No, this one aperitif was 12 hours
12.
because we had to cover the entire UV pay. Now wait half an hour and Tom will tell you all about it. These are the low far pointing. They were 8 hours if I remember correctly. Okay, another object similar. This is Marconi 11V. I thought a nice merger and AGN combination would do. And again, this is the MBSS. You see some structure here. This is first and last. You see the core, and the core can be an AGN there. And this is what you detect with the LOFAR, also with the longer exposure plus at lower frequency. And so then you see this structure much better, but yeah. And you also see that there is some counter part on the top. And this is the same, but overplot to an optical image. Using contours that the radio astronomer likes so much. They're not very sexy as a way, but they really tell you how much flux there is in each of them. So maybe we do something in the afternoon. And these two are image at even higher resolution. Yeah, sorry.
The pattern that you see in the images, is this just like a feature of the way that it's taken? In the bottom.
This one?
Yeah, that's
Yeah.
the next one.
These are featured because you don't have the full coverage. So this is real, this one are a problem. But again, if you wait half an hour, you will hear. These were just examples. So this one are observation at even higher spatial resolution. This is a LOFAR with the international baseline spread all over Europe. This is 0.3 of second resolution. We started from 45, so that's a big difference. And this tells you that in the center of this, there is actually a lot of extra structure, radio continuum. Complicated that we actually have no clue what it means, but okay. I wanted to show you also that in some cases, with some of the new radio telescopes, they can make a very large image. This is a mosaic of one pointing of aperitif. And you see here, this is 1 degree, so it's a huge field. These are all nice radio sources with also some problem. So if you look carefully, here is Markarian 273, this tiny object I just showed you, is up here. This is where we took actually the image I showed you before. These are some leftover artifacts from the data reduction. And if you look even more careful, down here there is F101. So in this image, you have, you can do science for, the rest of your life, certainly the rest of my life, but okay. So I wanted to now, so these were examples to show the variety. So you should pay attention when you get data, radio data from different surveys. What am I getting and what am I missing? So now I just wanted to tell you a little bit about the emission mechanism, because I think it's, of course, I don't want to give a full lecture, but just to remind you that there are two main mechanisms that can give you the radio continuum, the H1 another time. The radio continuum. One is thermal Bremsstrahlung, the free radiation, so just free electron accelerated. So this happened especially as a result of ionized gas around the supernova. So this is interesting for starburst, star forming kind of region if you study them. The luminosity depends on the number of ionizing photons, so you can get a lot of physics out of that. Please, if you are interested, there is this review of Jim Condon that, although it's 92, is still very much relevant. And one characteristic of this emission is that the spectral index that I showed you before, it's a power law. In this case, is typically very shallow. Here we are at 1 gigahertz, so one of the typical radio frequency, 5 gigahertz and 10. So is usually quite shallow or even inverted. So I'll show you an example in a moment. So this means that it's very seldom the dominant emission mechanism for radio continuous, with some exception, of course. And then the most important, I would say, is the synchrotron radiation, so relativistic electron accelerated around along the magnetic field. So this is what you need, the magnetic field, and relativistic electron, because the frequency of the emission depends on gamma, the Lorentz factor, and the magnetic field. So in order to get radiation at a few gigahertz, 10 gigahertz, whatever you need, gamma of 10 to the something, so relativistic. Okay, so one electron give you the emission at a certain frequency, like the symbol here. A population of electron, relativistic electron, give you the characteristic power of the synchrotron. So the flux that you measure is proportional to frequency to a certain spectral index. Just pay attention in the paper, whatever you read, whether it's minus alpha or plus alpha, because different communities tend to use different. Okay, so it's very confusing, but I'm sure you can cope with that, but just pay attention. And so a typical spectral index that you find is 0.7. So the slope of the power law in a log. And so this is great. This is great, but it's also not always a nice, clean power law. The electrons emit, so they age, and so they lose energy. So especially at the high frequency, they tend to, the power law tend to become steeper than at low frequency. But this is also interesting, because if you can measure the continuum, the shape of the continuum in your object at different frequency, and you see some steepening, the frequency where this break happens is proportional to the age of the electron, the last acceleration. So the older the electrons are, the more energy they have lost, and the more this break moves to the lower frequency. The lower frequency are the one that stays power law of 0.7 for longer, and then it gets steeper and steeper. So this is cool, because it gives you some age. That is always one of the complicated things to find in astronomy, the age of something. It's not trivial, but you can do. There is this signature. Okay, so in summary, you have these two mechanisms, and here I took what is definitely not the normal galaxy, but for now, let's be called normal galaxy, M82. So this would be the combined spectrum of M82 from radio to millimeter. And what you see here are actually three components. One is the dust re-radiating, but that's happened only at higher frequency for radio, so above 200 gigahertz, so almost the same. Then you have the part on the free, that is this component quite flat, as I mentioned before. So this component is actually mostly visible at few tenths to above 100 gigahertz. This is dominant only in this part of the spectrum. And then at more common radio frequency, let's say, the synchrotron dominated, that is this other component here. So in summary, the synchrotron can be the dominant mechanism. There are papers that I'm sure either you are aware or could be interesting that show how depending on the type of galaxy, the free can become more prominent. Dwarf galaxies seem to have this, I didn't know, but we have an expert in dwarf galaxies, so I learned. There are these two mechanisms. In most of the cases, the synchrotron will be dominant. In some other, the free could play a role. But in most of the cases, it is at the higher part of the radio frequency. Okay, so let's stick to the synchrotron just to finish off this part. Synchrotron, great, but who is producing this synchrotron? And so the thing is that the synchrotron can be produced both by star formation and by the AGN. And so depending who you talk to, they will tell you, wow, look at these guys with this nice AGN in the center and some other noise, a nuclear star formation. Oh. So I just wanted to mention this because I'm sure for this community can be relevant. So the synchrotron that comes from star formation is mostly due, again, this is what Condon writes, and if Condon writes, it's like the Bible. So, but these are massive stars forming supernova and H2 region. Of course, that is where the acceleration of electrons happen. But they also have a relatively short lifetime. But anyway, so if you see radio that could be connected to star formation, these are the objects that they can give you this. It means that you can use this radio to connect and to derive the star formation rate connected with this type of stars. So there are some cases where this is very easy to find. I mean, in this case, the contours, the optical image is obvious. The contours are the radio continuum. The lines are the polarization vectors. So if you study also the magnetic field direction. So you see that the radio emission nicely follow the region of the arms star formation. So you say, well, okay, that's star formation. So I go on and I measure the star formation rate from the radio that I can compare with that. Yeah, that's nice. Many people do. Of course, in the center, you can be affected by AGN. So you have always to really check whether 100% of your radio is from star formation or not. And I'm sure you are familiar with far infrared radio correlation. That is one of the diagnostics that people use to try to establish whether your radio emission that you measure is 100% from star formation or an AGN polluted. So then if it is only star formation would follow this correlation. If there is an AGN as an extra component, would put your flux, your radio flux or radio luminosity above this correlation. Yeah, I'm sure you are familiar with that, but I thought it was important to remember because in many cases it's straightforward, and in other cases the most complicated are a mix. And then if you establish a star formation, there is the star formation rate that you can derive. From this, there are different formulas, so that's just an example. Okay, so On the other extreme, there are the AGN, and when you are lucky, you have a nice AGN. These are the AGN that we really like, because this is the optical counterpart, these are the jet, the lobes, so they are so different in structure and so different in size that there is no discussion. So that's easy. Nice jet, very large. Of course, this is an extreme example. The complication, there are more normal cases like this one, but still, this is again the optical part, the red is the radio part. Again, much larger, even if you don't see the jet, because maybe they are not so collimated, but much larger than the optical, so there is no discussion. And in this case, you can even derive the spectral index of the radio emission and see which part has the older electrons. So derive a bit of the history of your radio emission. That's something that I like doing, and I think is very, very powerful tool. But just to not finish on a positive note, I wanted to remind you that there are this, actually the majority are this complicated case called radio white AGN, if you come from the AGN community, or called a very annoying AGN if you come from the star community, I don't know. But there are these objects that have the radio such that you cannot be sure 100% that it's really coming from an AGN, but you can also not say 100% that it's only star formation. So already in the 89, Keller defined this ratio between the radio luminosity and the optical blue luminosity. And depending on the value of this ratio, you can say my object is radio quiet or radio loud. So radio loud is above 10, this ratio, that I thought was a bit, but okay. So these are mostly radio continuum sources that are in the elliptical galaxy. As you have no, they are clear cut, they are AGN. And then you have this part, so-called the radio quiet, that still can have a part of AGN. So there, disentangling the AGN component and the star-forming component is the tricky one. And in most of the cases, this can only be done if you have a very high resolution observation, so that you can see mini jets, then likely AGN, or you can see lobes, but then you can also see ring coinciding with star formation, so you can read nuclear star formation. So you can, there is an entire community working on this. If you have any question, go to Annelies. So anyway, this is just to give you also a feeling that if you get radio data, you can do a lot, but you should also be aware of few complication, as always, obvious. So I think this was my part, Tom, was it? Yeah. So, and so the second, so maybe if there are questions, we should stop for a second.
So the only way to tell apart is morphology.
Sorry?
The only way to tell apart AGN from star formation is whether you're looking at spiral arm or you see jets. That's
well, there is the radio infrared correlation, that's one.
right.
There is the radio luminosity also, if it is very high, that's, but in a way it's connected with the radio infrared. And there is the morphology. The morphology is high resolution morphology, typically, because usually these annoying radio white or mixed objects are small in radio. So if you take an MVSS image, it will be just a blob. Maybe even a first image, 5 a second, would be just a blob. So you have to go really to sub-a-second. Yeah.
But here in both cases of AEN and star formation, we are talking about synchrotron radiation.
Yeah.
So isn't it possible to disentangle using this break on the power law spectrum?
Well, yeah, so if you manage to have many radio frequency, you can do something more subtle. That's true. Usually you are not in that luxury situation in general. I mean, unless you plan, of course, a project such that, I don't know, the VLA can do many frequency using many configuration, matching the size, so you could do the spectral index. But then it's difficult to get only from public survey. But yeah. We can, yeah.
You were mentioning age of electrons.
Yeah.
What does that trace in physical terms?
So trace the age of the last reacceleration of the electrons. Think. Yeah. So, for example, in this object, so this is where the core is, the black hole, the AGN, I don't know. That's there will be two jets, you don't see here. They go, and here there will be the region where the jet hit the interstellar medium, intergalactic in this case. And here is where the spectral index is also flatter because they get reaccelerated. And then they lose energy and become steeper. So from how steep it is and which frequency steepens, you can derive an age of when this happened. So usually it's 10 to the few times 10 to the 7, 10 to the few tenths 10 to the 7 is a typical age of a radio source.
AGN and certainly the radio are variable. So there's a quiescent phase, and then the AGN becomes radioactive in the radio emission sense, but then it stops. And then from the spectral index, you can estimate the time since the AGN stopped, for example. So they are highly variable with very short time scales.
You can apply in different ways. Again, I didn't say too much about this because you need a multiple frequency to derive this break, especially the break if you want to derive in different position, that depends. So it's something that usually needs some ad hoc observation, but it's something very powerful, I find. Personally, I work on that, so what can I say? Yeah. But it's something that the optical people don't have, optical AGN, so I like it. Okay, but so now you get the full Monty almost. Yeah.
Now, the rest of the talk is technical. Say, how does interferometer work? And I will try to point out a few aspects in which radio frequency is very different from, say, optical imaging. There is a few characteristics that it's a completely different domain, and I will highlight a few of them, not all, but a few that I think it would be helpful that you were aware of, that it's a completely different business. This book is sort of a standard reference on interferometry. Everything you want to know, and even more, is in the book, and it's open access. So if you Google to Springer on this book, Thomas and Moran and Svensson, you can download the PDF. So it's open access. So, and this is, I think, the standard reference of interferometry. Why interferometry? Well, it's obvious, of course, it's because of the need for angular resolution. We all know that the resolution of any optical instrument is lambda over d. And because lambda is very large, say even in MOPA, it's 30 meters. To get to the right angular resolution, the size of your instrument has to be very large. Just to set the scale, to get a resolution of 1 arc second at 1.4 gigahertz, 1.3 gigahertz is the H1 frequency, you need a telescope of 40 kilometers. So this is obviously not feasible. So we have to do a trick, or even a few tricks. And the basic is the following. If you have say a mirror, an optical telescope, you have a mirror, light falls on the mirror and goes to the focus, and there is all the radiation is combined. So in the radio, you can do the following. You can cover the same area with all small dishes. Each dish picks up radiation. and then you connect them with the cable, and you add through the cable. So in essence, you do the same thing. And the only thing the mirror does is to combine the radiation and the focus. And with radio telescope, you can just do it through a cable. So in principle, you could cover this area all with dishes, small dishes, and combine them electronically. Obviously, still you have to fill this aperture of, say, 40 kilometers or even more. So that's still not feasible. And it's 25 million dishes covering an area of 40 kilometers. It's not feasible. So there are two basic things that you do. And the concept is called Earth rotational aperture synthesis. Aperture synthesis means that through the combination of dishes, we synthesize an optical aperture. And the other thing is we exploit the rotation of the Earth to fill the aperture, basically. So the first thing is, instead of covering this full 40 kilometers, we leave out dishes, because simply we cannot. We can only afford to build, like in Westbrook, 14 dishes, or Omega 64 dishes, there's simply not more money to build more dishes. So we leave out dishes, but still we keep the 40 kilometers. So we lose, obviously, sensitivity because we lose collecting area, but we keep the same resolution. See, the level over D is still high. Of course, this is a telescope with holes. Conceptually, it's like a mirror optical telescope with many holes in it. So the optical imaging performance is terrible. The images are terrible. But we can fix later in computer because we know where the holes are and we can correct for it. So that's one thing. Just a few dishes and we combine them. And each dish is combined with another dish. So, for example, Westerbork has 14 dishes, means that there are 91 combinations, n over n minus 1 over 2. The second trick is that we exploit the rotation of the Earth. So imagine this is conceptually, say, a telescope like Westerbork. These are the dishes on a line, as seen from the source. And because of Earth is rotating, the source sees this. And simply because the Earth is rotating, the orientation of the telescope, of the array, changes with time. Simple like this. And what we do, so it takes 12 hours, say, to make full circle, or half circle, sweep 180 degrees, and we add up all these measurements. So exploiting this rotation of the Earth, we can create a two-dimensional aperture. And this is the Earth rotational aspect of interferometry. So each interferometer has a number of dishes, and you observe several hours in order to create or to fill up your two-dimensional aperture. So Westerbork is a one-dimensional array, but you can create a two-dimensional aperture by just being patient. 12 hours, you fill up the two-dimensional aperture. So this is the essence of interferometry. How does it work? These are two antennas and they are pointing in a certain direction. One difference with optical is we don't detect the photons. An antenna detects the electromagnetic field. So there is an antenna here, say with a dipole, and what comes out, and if in the case of monochromatic radiation, is a nice AC, alternating current from the receiver. Yeah, so each antenna detects a current. Not a photon, it's not photon counting like the CCD, you detect the current. Obviously, the stronger the source, the stronger the signal. So one aspect of what you detect is the amplitude, the strength of your source. But an interferometer detects another quantity, namely, this antenna is closer to your target than this one. So there is a time difference. This is the wave amount coming from the source, and there is a time difference between the arrival at the two dishes. And the wavefront arrives earlier at one dish compared to the other dish. This is a time difference, but you can also say it's a phase difference. There is this sinusoid coming, and just the angle, say the sinusoid, is different here than there. So there is also a phase difference. So the output depends on two things, an amplitude and phase, an angle. So the output of this, what happens is the signal of this one is cosine term, and the signal of this one is multiplied and averaged over time. That gives what is called the visibility of the interferometer. And because it contains an amplitude and phase, you can represent it as a complex number. And a complex number has an amplitude and a phase. So what comes out of the interferometer, what we call the visibility, is a complex number depending on the source. And in a sense, the amplitude gives the strength of the source, and the phase gives the position. Because if the source is in a slightly different position, this time difference, and hence this angle, this phase, is different. So phase, in a sense, gives position, amplitude gives the strength. And that's represented in this complex number called the visibility. And this visibility here, I've written here, visibility depends on the coordinate U and V. U and V is the coordinate system in which the antennas live. So these represent the separation of the two antennas as seen from the source. So it's projected separation. And you could represent it in meters, but the standard unit of U and V is wavelength. Because the natural unit of an interferometer is wavelength, obviously. So these are U and V represent the relative positions of the two antennas, not the absolute position, just the separation between the two antennas. And this is the, say, the space in which the telescopes, the dishes, live. If you do the math, what turns out that this visibility that you measure is the Fourier transform of the brightness distribution of the sky. And this is the brightness distribution of the sky. This LNM is a coordinate system on the sky, centered on your position. So it's L and M, radians in a sense. Turns out that this visibility that you measure in this way is the Fourier transform of your image. So the whole idea of interferometry is to measure this visibility for a very large set of U and V, a large set by having many dishes, so many combinations, and wait a long time to sample this aperture plane. So we collect this visibility for a large number of UV positions, and then in principle you can do the inverse Fourier transform to make your image. So you measure the Fourier transform of the image. So after moderation, you don't have an image. The optical camera open, camera close, image. This is not the image, is not there yet. And you make the image after the fact, after the observation. And in fact, you can make many images of these observations. I'll come to maybe on Thursday. So the idea is to measure it for a large number of different telescopes and different orientations. Just to illustrate this Fourier transform concept, this is an example of 2 point sources on the sky. And this is the Fourier transform. So these are these UV coordinates, the separation between the antennas. And you see that it's a nice sinusoidal pattern because the Fourier transform of 2 point sources is a sine function. And the period of this sine function depends on the separation, of course, of these two. And also the orientation of the sine pattern depends upon the relative orientation of the 2 point sources. And our telescopes move in this space. Our baselines move in this space. Now you can see this here, lambda. Usually we talk in the units of kilo-lambda. It's a typical unit, 1000 lambda. So the observation takes place in this plane, and then with the inverse Fourier transform, you get the image.
So it's not deterministic because you're not fully covering that space.
Next slide. Yeah, completely correct. So this is the Fourier transform of the true sky. Obviously, like I said at the beginning, we have a terrible telescope with large holes. So this is an observation. This is from Compact Ray in Australia, using 5 dishes. So there are only 10 baselines. And over time, it's also east-west array, over time, in the 12 hours, each baseline moves along an elliptical track in this UV plane. Every 5 seconds or 10 seconds, making a measurement of this visibility. Okay? So these are your data. Okay. So instead of measuring this, we measure this. And these are the red dots, are the positions of the baselines at the beginning of the observation, and during the 12-hour, they move, like I showed before with the red dots. They move through this plane. So this is the information we have. So it's very poor. So our optical imaging instrument is very bad. But okay, we have something. Clearly, I managed to go back here. Yeah. Clearly, we have a relatively very poor coverage of this UV plane. So the UV coverage is a very important concept in interferometry. Yeah. A very important concept is to improve this UV coverage. Obviously, one way is to have more dishes. So this is why Alma has 64. So you have a much better UV coverage already to begin with. So this is another illustrating this UV coverage. Again, if the Earth moves, then you start off filling simply because seen from the source, and Earth is rotating, the orientation and also the projected separation of the two changes with time.
But you always need the 12 hours.
No, well, in principle, you do not need. But the longer you do, I'll show an example, the longer you do, the better it is. Also, the examples I've shown are for east-west baselines. So in a sense, at any instant, you only have a one-dimensional telescope. Those tend to be built in the 60s and 70s, previous century. Modern telescopes have a two-dimensional arrangement. So the instantaneous coverage is already better. You already have a two-dimensional telescope. So it has to do with money and also computational capacity. Because making the image requires quite heavy computations. Okay. The visibility is the Fourier transform of the sky, so we can get the sky through the Fourier transform of the visibilities. One interesting thing is you combine telescope 1 with 2, but then you also combine 2 with 1. It sounds like an irrelevant detail, but you occupy the opposite point in the UV plane. So if telescope 1 and 2 has coordinates UV, 2, 1 has coordinates of -u, -v. So every observation, every single time step, you get 2 points in your UV plane. And the thing is, the amplitude is of course the same, but the relative arrival time is opposite. So the phase is opposite. So if you measure in one point of the UV plane, the phase, automatically at the same time you measure the same visibility but with the opposite phase. So when you do this sum, this is basically the sum, you sum the visibility -u -v and u and v, and they have the opposite phase. So if you add those two, you only have the real part, because the imaginary part has opposite sign. This also has to be because our image has to be real. And we do a Fourier transform, and these are complex numbers. This is a complex number, but this is real. So this was called the Hermitian property of the visibility is needed. So effectively, this Fourier transform, say in the discrete case, because we don't have a continuous case, the image is just the sum of cosine, two-dimensional cosine patterns. Yeah, this is just the discrete version of this, exploiting also this symmetry property. So the image that you make is the sum of sine waves. So for each visibility, you take a sine wave with a period and an orientation corresponding to the UV coordinates of that sample. You multiply that with the amplitude of the visibility, and you shift it with the phase of the visibility, and you plonk it on the sky. And you do that for every visibility. I'll skip this. This is, yeah. So what you have, and this is again the sun, this is the sky, see, LM, and this is a two-dimensional cosine pattern on the sky corresponding to one particular visibility. A relatively short baseline because the period is large and a certain orientation. This is another baseline, a longer baseline because the period is faster, etc., etc. So these, for each visibility, you put this on the sky. And by doing all these visibilities, you get the image. So this is an example of this. And this may also be your question on the last page. Here we have two antennas, one measurement, say 1 into base time, 10 seconds, that's it. So this is the UV point of the measurement, and this is the offset emission, and it generates this two-dimensional sine wave on the sky. 5 antennas. I created 10 combinations, plus, of course, the symmetry, so there are 20 points here. So this is the sum of 20 two-dimensional sine waves. And each has a different orientation depending on where the visibility is in the printing. So this is 5. This is 11. And this is 27. So this is 27. This is example taken from the VLA. This very large array in the US. The array configuration is a Y. So the instantaneous coverage of the VLA is this. And this is also the coverage of the FLAS, because the FLAS survey is an all-sky survey, but they spend only 1 minute or so, 2 minutes per position. Because if you want to do the whole sky, you cannot afford to do more, obviously. So you see the UV coverage is quite poor, and every UV point contributes a line. No, because it's the sum of these two-dimensional patterns. Of course, each visibility has a noise, has an error. So the noise in the image also has these stripes. So these stripes that you saw in the velocity image, and in the first, are due to the poor UV coverage. Because the noise is not a nice circular Gaussian blob. The noise of every visibility is a line, are stripes in the image. So this is typically the sign of a snapshot observation, because of the poor UV coverage. So this is 27 antennas. Now we observe what is it, 2 hours. And due to the rotation, this pattern that we had before, this pattern is rotating, filling up the UV plane, and showing an improvement. And you start to see the sources. This is 2 hours. This is 4 hours. Now this looks like an image. And this is the image, simple, but you can see all these artifacts, all these stripes and circles are due to we have a bad telescope. And so this is what we call the dirty image. It's really a dirty image, and it fully contains the imperfect imaging capabilities of an instrument. But we have an image. We have sources on the sky, and we have obtained an image with a resolution of a telescope of the size of VLA, in principle 30 kilometers. One important thing to realize, what is called the negative pole. Two antennas cannot be in the same place, obviously. So the shortest baseline that we have is larger than 0. At least twice the diameter of the dish, probably more. Say typically it's 20, 30 meters, the shortest baseline. Well, look at what happens. Our visibility is the Fourier transform. Let's put in UV coordinates 0, 0. Now, 0, 0 here. So the visibility at 0, 0 is the integral of the image. It's total flux of our image. But we don't measure this because we don't have two antennas at the same place. So if you make an image, a dirty image, and you add up all the pixels, you get a 0. So an interferometer does not measure total flux. Yeah, total flux of the dirty image is 0. You have to realize that. We can fix it, but so, for example, this is a dirty image of a random observation of a source. Look, everything blue is negative. So here's the emission, and it's surrounded by large negative regions. It has to be because the sum of all pixels is 0. So the positive source has to be compensated by negative regions on the sky. Can be fixed, but be aware of this. Another aspect of this is that, in a sense, an interferometer is a spatial filter. And there are structures on the sky that you do not measure because there is no baseline there. So the lack of short baseline can pose a big problem, because an angle is lambda over d. So a structure of a certain size on the sky corresponds to a length of d lambda over the scale. So large-scale structures, for example, are only visible on short baselines. And the typical Fourier property, something large in one domain is narrow in the other domain, and vice versa. So you have a large structure on the sky. Your Fourier transform that is something very narrow, and these vertical lines are where the baselines are. And we don't have baselines where there is the Fourier transform of our very large structure. So we do not measure it, so it's not in our map. Typically, this is not a big problem. For example, for the typical telescope delay, that's the work we have got at 1.4 gigahertz. This starts to become a problem for structure larger than 10, 15 arc minutes. So very large scale. So your typical galaxy, it's fine, not a problem. But you can run into some very interesting problems. Very nice example. This, the problem is due to RFI, man-made signals corrupting your measurement. This is from America, South Africa. This is frequency from 800 to 1700 megahertz, so very broadband. And this is time. And you see all these wonderful black vertical stripes. This is GPS. This is satellite telephone. This is our GSM. So at certain frequencies, you cannot use your observation. So you have to flag for these frequencies, you have to flag these data. They do not contribute to your image. The problem is that this impact of RFI is stronger on short baselines than on long baselines. So if you flag in these regions, you flag short baselines. But here you keep them. So your spatial filter is frequency dependent. This is a wonderful example. This is a wonderful radio source. There's a jet here, in two lobes, big lobes, perpendicular. This is Meerkat. This is a broadband image from 900 to 1700. But because of this frequency dependent flagging, in this frequency range, all the baselines shorter than 100 meters were removed from the data. Well, 100 meters corresponds to about 3 arc minutes. So that flagging removed all structures larger than 3 arc minutes in that frequency range. So if you make images, so this is a total band, if you split up that total band in several subbands and make an image for each subband, you get this. This is the low frequency, 1050, 1160, 1260, 1340. And you see nicely this big structure, but it's gone here. It has disappeared because of this flag. Because this is the frequency range where this LFI happened, and we flag the short baseline, and we remove this wonderful source.
So you're forced to discard the frequencies, you cannot model them in any way that can help you.
Depends what you want. If you're interested in this blob, yeah, you have a problem, because it's not there, so you cannot measure anything. If you're interested in these point sources, then they are not affected. You also see it's not even this blob, also this source is skinnier than it is at these frequencies. So even that source loses structure. So we will be aware of this flagging RFI, which is very severe, and because of this GPS. GPS is everywhere. You can go to the middle of the desert in Australia, there's still GPS. So this, wherever you go, this is a problem. Every telescope in the gigahertz range, and it's become more and more problem at higher frequencies. Thanks to Elon Musk and all these people doing all this satellite internet, etc. It's a huge problem. And this poor UV coverage, this was the slide that Abel also showed. These stripes, etc., are also due to that. The fact that you don't see this extended emission. And this is the long observation with Westerbork and Hova, nicely, and this line here corresponds to this structure here, so beautiful image. That you don't see in these two, part is sensitivity, but part is also this UV coverage. So even if plus and first would a little bit longer, they still would not see it, because we don't have the short baselines. So it's two effects. One is noise, signals noise, sure, but also UV coverage is a factor. I would have there.
You should ask them how they cope with the.
Sorry? Oh, perfect. Deconvolution. So, as I said in the beginning, I want to highlight two aspects that are really different in interferometry compared to optical imaging or infrared imaging. And one is what we call the deconvolution. And the deconvolution is the process that takes care of the fact that we have a very poor sampling of the aperture plane. And somehow we have to find a way to fill up these spaces that we get this. Yeah, so we only have measurements on these tracks, but we need a process sort of to interpolate into these empty spaces. And that's called deconvolution. And I'll try to explain how that works. So the true image would be this, the Fourier transform of the visibilities. And this visibility is the visibility of the true image. But we don't observe, obviously, we don't observe all these true visibilities. What we have, in a sense, is these true visibilities multiplied by what we call a sampling function. And the sampling function is 1 where we have a measurement and 0 where we don't have a measurement. So what you see here, grosso modo, this is the sampling function. It's 1 along these tracks and it's 0 in between. So what we measure is the true visibility multiplied by this sampling function. And then we do, to make the image, we do the Fourier transform. Well, the Fourier transform of a product is a convolution of the two Fourier transforms. So what we get, it's called the early image, is the true image convolved with the Fourier transform of our sampling function, or in other words, the PSF. This is the PSF, this is the point spread function. So our image is a convolution and convolved with the Fourier transform of this sampling function. So what we have to do is to deconvolve, take out this effect. There are a number of ways, but, to show. So this is for the Westerbork. This is a full 12 hours of Westerbork. We count 91 baselines. So this is the UV sampling, and this is the dirty ring. Nice circle, very characteristic of east-west rays. And because east-west rays, UV coverage, are always these nice ellipses. So Fourier transform also has ellipses. This is very characteristic of Westerbork and compact ray. So if you have, and this is again the PSF, so every source in the image is involved with this PSF. So every source here in the image, and these are point sources. Each of these point sources is represented in a map by this PSF. You see, every source has this set of rings around it. And this is the effect of the imperfect sampling of the UV plane. And the image is just the sum of all these PSF responses centered on each source. Classic algorithm to do this is really a very simple algorithm conceived by Herco in 1974. And the technique is very simple. Everybody could have thought of it, but he was the first to do so. So we have your dirty image. Let's go back to the dirty image. Yeah, you go to the strongest technique. Let's say it's this one. You say, okay, this is a point source. You model it as a point source, a delta function. And we know the response of a delta function in the image is simply this point spread function. So what we do, we take our computed point spread function, and we can compute because we know where the telescopes are and where they are not. We shift this pattern to this position, scale it with the flux of that source, and subtract it from the image. Meaning that that source and the rings have disappeared. So then, on a piece of paper, I write this position, I have a point source of this flux. Next iteration, you go to the next source. And the source, which is then the stronger source, after subtracting this one, and you do the same. So you write down second source, this position, this flux, etc., etc. This is in action. So this is the dirty image. And you can see there are a few sources here, and there's an extended source here. And each of them has these rings around it. This extended source, of course, because it's extended, the rings have become fuzzy. It's because the source is fuzzy. What you see here is iterating this process. It goes in the beginning of the movie, it goes to the stronger source, shifts the PSF to that position, subtracts it. Then the second brighter source, etc., etc. And you see slowly the sources and the rings disappear. So after this process, I have an image where all the sources and all the PSF structures have been removed. Plus, I have a list of positions and fluxes of point sources. So once I decided I've removed everything from the image, I stop, obviously. Then I take my list of point sources, I put them back in the image. I don't put in delta functions, that would be unfair, because we have a telescope with a certain resolution. Our telescope, a point source, doesn't see it as a delta function, so you smear it with small Gaussian that has the size of the spatial resolution of the telescope. This is called the clean image. Clean being clean image. So every source, every delta function that you find is represented in this image by a small Gaussian with the size of lambda over d. So after this iterative process, all the rings have been removed and we put the sources back, and now we have the image. Problem solved.
So your PSF is a mathematical function, so you have to leverage.
Our PSF,
So you build it from.
we know exactly the sampling functions. We know where we have data, collected data. So this is just a map of 0 and 1 sampling function, and you Fourier transform that. So it's the theoretical response, the theoretical response to a point source or unit flux. Yeah, point source of unit flux, the Fourier transform is one everywhere. So it is one along this tracks. Your Fourier transform, so a unit point source would look like this. So it's a theoretical concept. If your data are not well calibrated, the actual PSF in your image will be different because there are errors here.
Yeah, that's what's my.
Different. We'll come to that on Thursday.
Calibrated, you mean the distance between the telescope?
No, also, just a prelude to Thursday, I measured this difference in arrival time. One dish, other dish, geometric delay. You can calculate so many meters, wavelength. This is the time, so phase. This is only true for a perfect straight wavefront. But of course, Alma, water vapor, low varying ionosphere, this wavefront is not straight, it's curved. So this arrival time is affected mainly by the atmosphere or the ionosphere, depending on wavelength. And the calibration you do is to correct for this effect. So the calibration is in fact mainly to straighten the wavefront. Thursday I'll show a few nice examples of that. That's the calibrator. Of course, you need some calibration. Because you measure the output on a pen in volt or whatever unit, you will have to convert that to some astrophysical ergs per square centimeter per second, etc. Of course, you go to a calibrator and you know how strong it is. That's one type of calibration. But actually, the calibration for actually image quality is mainly for correcting the distortions in the wavefront. That can be very dramatic. Alma, the high bands, is terrible. Low-VAR, low bands, maybe even worse. I'll show a dramatic example on Thursday. But okay, you assume a perfect calibrated image, antenna, because we haven't done this calibration yet. One aspect other that's different for interferometry is that in the end, to calibrate this effect, you use the data to calibrate itself. You don't use an external calibrator, it's called self-calibration. But you haven't done that yet, because to start this process, first you need an image. So the first image we make is not well calibrated. And this is the screening process.
Tom, can I ask, how many sources have you calculated this for in this example?
Oh, this, you typically you keep on going until the maximum, and you subtract sources. So what's left after subtracting sources is we call the residual. Then you look at the peak of the residual. If that is still 10 sigma, you continue and you say stop until 1 sigma, 2 sigma, whatever. Yeah. So you define some criterion that says my image is empty now, except for noise, and then you stop.
And how many sources are we talking about?
Oh, depends. Well, there's one thing I did not mention, small detail. What I said is that each iteration we ship a new source, we take its amplitude and we subtract it. This is not really what we do. We use a sort of damping factor called the loop gain. So if there is a source of 1 Jansky, we subtract maybe 10%. So 90% is still left. So maybe it's still the strongest source, then the next iteration, this 90% will lose 10%. This is pure for numerical stability. It's not really, in essence, part of the algorithm. In principle, you could use, say, this loop gain, take away 100%, but then numerically it is less stable, so you damp it. So the number of components that you find is much larger than the number of sources, because each source can be represented by tens of these delta functions. Well, it depends on the size of the image. A lower image is many degrees by many degrees, so huge number.
Do you need some reference or you just go blind?
No, this is you do the self-calibration.
Okay.
It was not on the program, but if you want, I can, not now, but maybe on Thursday. You use the data yourself.
The component can be thousands.
Or millions, can be millions.
No, so
Yeah.
So the problem with imaging, so I've got to show this profile. Each antenna is a stick with 4 wires. Okay. preference on type of technology schemes. All the technology is data. The data volumes are enormous, many, many terabyte per observation. So all these computations so all the technology in telescopes like LOFA is in the computing, not in the telescope anymore. And it's a huge computational task, and in principle, LOFA can keep an observation only for a limited amount of time. Otherwise, it's too expensive to keep all these petabytes per year. So, computationally, this can be an extremely heavy thing to do. And this is, I think, the limitation of imaging. SCA, coming soon, this is the limitation. You as a user will not be able to do this anymore because you will not be able to afford a computer to do this. So it can be an extremely heavy computational load. But somebody does it for you. That would be good. So just to wrap up, so back to these two consoles that I had earlier. This is the 30 image. All these rings, because we have only sampled UV data along these tracks. This is the image after the clean. And so all these rings have been removed using this iterative clean procedure. Now it's very instructive to see what happened in the UV plane. And this is the original observation, and only data along the tracks. And as I mentioned, the clean, we have to find an algorithm to interpolate. If I Fourier transform this clean image, so after the deconvolution, you can actually indeed see what happened. It filled up the spaces in between. The empty spaces are now filled up using this iterative clean procedure. So we have solved the problem. And another consequence is, as I mentioned before, because we don't measure at 0, 0, the total flux of our dirty map is 0, but you see clean also interpolated to 0, 0. So now my clean map, if I add up all the pixels, I get a number and I get the total flux in the image. And so this means that the way you measure fluxes is now, you can now do a normal way. You could just add a bubble and I'll first get your number. You cannot do that on your dirty map.
But do you still see rings then?
Sorry?
Or do you still see rings on the...
Because it's a good question. Because the noise is only on the rings and not, well, in the sense that there is noise on these, but it's spread out much more. So this, you still see the rings because that's where the noise in the observation is. And the noise in the interpolated regions is not visible. So that's why you still see, it's not because the signal is stronger, it's because it's noisy. Yeah, it's a good point. This I will skip, I think. Yeah, one last slide, this is the last slide. If you have a large image with very extended sources, this clean algorithm, where you represent every source as a set of delta functions, can be very inefficient and takes a long time. If you have quite an extended source, every pixel delta, and also this loop gain, you subtract only 10%, so it's not very efficient. So we do something else. Say the clean, as I explained, is that your image is a sum of delta functions convolved with your Gaussian. But you can also say, when I find a maximum, I look at two things. One is how strong it is and how large it is. If it has a certain extent, I do not represent it with a set of delta functions, but some Gaussian, for example, of a certain size. That's obviously much more efficient to represent an extended source than all this set of delta functions. So what you do is you define a set of scales, delta function, small, larger, 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 and for each maximum, you find out how do I represent this source as a delta function or a small Gaussian or more. And obviously that's much more efficient then, and it turns out it's also more accurate. Because, the problem with this clean algorithm is you can only find delta function where there is a pixel, not in between pixels. So if there is a point source that on the sky is actually in between pixels, and it is a point source, clean cannot represent it. So this adds a lot of physical flexibility to the clean algorithm, and so it's faster and more accurate. So this is the standard clean that people use. So in CASA, it's in a famous program, WS Clean, it's called the multi-scale clean. So this is the standard way of doing it. So it's a variant from the original Hurtog clean from 74. In essence, the same, except there's a bit more flexibility in representing sources in components. I think this is UV sampling, crucial. I will later, Thursday, we'll come back to it a little bit. Be aware with these snapshot surveys like FLAS and FIRST. In particular, FLAS has a very bad UV coverage. It only sees point sources. So if you are interested in a nearby galaxy, forget it. You will not see a star formation. You may see the AGN in the center. So if you want to find out like the radio spectrum, don't use FLAS. First, similar problem. Of course, high resolution, so you can see is there an AGN or not. But be careful with interpreting images with poor UV coverage. Or, for example, as this example that I showed is flagging because of the GPS systems. And you apply a spatial filter, and actually the source disappears from your image. It's not there. It's a beautiful source. It's like the Fermi bubble, but in a different galaxy. It's a very interesting source. Oh. One thing that I have not mentioned a lot, one thing I mentioned is that the image in the end is just a sum of cosine waves in the image, each with a certain orientation frequency. And they are weighted by the visibility. I can do another thing, is that I can give, for example, more weight to the longer baselines than to the shorter, to stress resolution. Because if I give more weight to that longer baselines, the PSF will be a little bit smaller. Or I give more weights to the shorter baselines, so I pump up the large scale, faint, low surface brightness emission. So there's something called weighting, that I can tweak, in a sense, the image by changing the resolution and the noise level to what I'm interested in. If I'm interested in faint, extended neutral hydrogen around the galaxy, you should weigh the shorter baselines more than the long ones. If you really want an image high resolution than AGN, you do the opposite. So that's a weighting, and there's no time to discuss this, but that's another important. So this robustness, where you see in papers, we use the robust half. That's a consideration. What do you want to stress? You can do both, of course. It's not forbidden to make more than one image from the same observation. You can make one image stressing the large scale and one image the fine scales. You can do both in between, whatever. So nobody will get angry. But be aware that there is a tool that you can play with to sort of optimize your image for what you're looking for. Okay, I think this is getting time. Okay. Yes.
If I understood correctly, in the clean of the image, you subtract your PSF that you compute theoretically from your UV coverage, right?
Yes.
And then you substitute that PSF that you subtracted with delta adapted to your resolution.
Correct.
But you could theoretically, I guess, compute the PSF that you would have with a perfect UV coverage, right? The same way that you compute it for your specific UV coverage. So wouldn't you use that PSF with that fully coverage for substituting the...
That's effectively what you do, because there's a lot of things that I didn't mention, but when you do the Fourier, inverse Fourier transform,